Hey everyone, today we're going to talk about a particular type of vector field called a conservative vector field and some of the ways that we can check to see if a vector field is conservative. I guess what a conservative vector field actually is, and then how we can, we'll work through some examples where we determine whether or not a vector field is conservative, and then also recover its associated potential function, which I will also define just here in a second. Okay, so conservative vector fields are just a really super nice version of a vector field that have, well, a very particular property. And that particular property is that this vector field, which, if we can think of it as a function f, this had to have come from a gradient of some other function. We'll call it little f. So if this is our vector field and it's conservative, then, well, it's considered conservative if it came from a gradient. And this function that it had to have come from is called the potential function for the vector field. So main idea here is that it's possible to figure out a function it came from. Okay, so and there's an easy way to check whether or not we're able to do this, whether or not it has this really nice property, and that is in the 2D case. We look for f1, its partial derivative with respect to y, to be equal to the partial derivative with respect to x for its second component. And then in the 3D case, we don't have quite an easy time, but it's still not too terribly bad. We take what's called the curl of the function, which is, or the curl of the vector field. And that's when we take this gradient operator, and I'll kind of show you what that looks like. And we take the cross product of that with your vector field. And well, this guy right here, we think of this as being just a vector that only contains our partial derivative operators, not the partial derivatives themselves. And just a quick note, sometimes what you'll see is just like the partial sign with a little subscript. That's the same thing as the partial derivative operator. But anyway, when we take this crossed with f, the idea behind this, we're just, you do the determinant of I hat, j hat, k hat, and then we put our partial derivative operators in here. And then our components of our vector field. So no gradients have, or no partial derivatives have been computed yet, but working this out, you'll compute a bunch of partial derivatives, and if it comes out to be equal to the 0 vector, then you know that you have a conservative vector field. And that's pretty much all there is to checking to make sure you can do that. Now, one option that you might wonder about is, okay, so we have this, we're looking for a potential function, and we want to just check to see if we can, start with a gradient and then work our way backwards to a function. Well, you may recall in a video that we did a while back that we're able to do that. We can take a vector that has a bunch of functions in it and then try to put it back to the original function that it came from. And we'll wind up using those techniques to actually find the potential function. And it may be tempting to just, take a whack at it, see if something pops out. And I can tell you that if the potential function actually doesn't exist, you will have wasted a ton of time for absolutely no reason. So always check this first, and then you can find your potential function after that. And I'm going to go ahead and put this in a box. This is a nice little test. So the examples that we're going to look at today are going to be performing this test on it to determine whether or not we have a conservative vector field. And then if we do have a conservative vector field, we will find the associated potential function. Determine whether the following are conservative vector fields And if so, find its potential function. All right. So for this one, our first example here is going to be the vector field with x 0, 0, like so. And the way, since we have a three-dimensional vector here, we're going to work with the cross product. So we're going to check that, we're going to see what this gradient type operator crossed with f turns out to be. So we have I hat, j hat, k hat, and we'll have a partial with respect to x, partial with respect to y, partial with respect to z, and then x 0, 0 there. So what is this equal to? Well, we have I hat times, and now we're just taking a determinant. So it's the partial of y with respect to y of, no longer times, since this is really kind of, we're thinking about this as being like an operator, or like it performs this operation of taking the derivative. We're not multiplying by 0. We're taking the derivative of 0 with respect to y, and then minus the derivative with respect to z of 0, minus j hat of, now we're going to take the derivative with respect to x of 0, minus the derivative, derivative with respect to z of x. And then plus k hat times partial with respect to x of 0 minus partial with respect to y at x. So, well, that's just going to be zeros, because when we take the derivatives of the zeros, we just get 0 back. So we have 0 I hats minus, this is going to be 0, derivative with respect to x of 0 is 0. And then this is the derivative of x with respect to z. So since there's no z in there, it gets treated like a constant. So that's also going to be 0. And then plus, that's going to be a 0. And then right here, minus the derivative of x with respect to y. So that's going to be 0 as well. So we do indeed have a conservative vector field. So now at this point, this means that there is a potential function to find. Remember that this is such that f is, or capital F is equal to the gradient of our little f that we're looking for. And I guess I need a new page for this. Okay, so the idea here is that we are recovering a little f such that f is equal to the gradient of f. So we are recovering a function from its gradient. Now, we've done this several times in the past, and I've got a video from earlier in the semester where we go through several examples of this, but I know it's been a little while, so if you're feeling a little bit rusty on how to do this, I highly recommend that you go back and take another look at that video and just kind of refamiliarize yourself with this process. So, but just the main idea here is that we're going to wind up taking the integral of each of the components of f. So remember that our vector field is given by x 0, 0. So we're going to have that f of x, y, z is equal to the integral of x dx. And if I take this integral here with respect to x, I'm going to get 1/2 x squared and then plus some unknown function in terms of y and z. I can also use my other two components to get information about f and take the integral of fy with respect to y. And that's just going to be equal to, well, 0, because when you integrate 0, you just get 0 back. And then plus some unknown function in terms of x and z. And then integral of 0 here So we're going to get 0 plus some unknown function in terms of x and y. So putting all this information together, we look at the integrals that we took with the y component and the z component, these last two pieces here, and they really don't add any new information to what we got when we took the integral with respect to x, and we're covering that piece right there. So really, this is all the information that we need. This is going to be equal to 1/2 x squared, and then plus just some constant, I'll call it little c. That guy's a constant there. So, because, I mean, just a constant isn't really able to be recovered here at all. Let's look at another one. This one's really quite similar, but slightly different. We're going to say that our vector field is equal to 0, x, 0. Super close to the other one, except now we have the x variable in the y component slot. And we're kind of wondering if, will that make a difference? Let's take a look. So to figure out if this is conservative, we check our gradient type operator crossed with g. And that's going to be equal to I hat, j hat, k hat. And then our partial with respect to x, partial with respect to y, partial with respect to z. Whoops, there we go. And then we have 0, x, 0. All right, so my determinant here is going to be equal to, so I'm doing I hat first. So I'm going to have partial with respect to y of 0 and partial with respect to z of x. So again, not multiplying, we're taking partial derivatives there. All right, so minus j hat, partial derivative with respect to x of 0 and partial derivative of z, or of 0 with respect to z. So, and then finally, k hat is partial derivative with respect to x of x minus partial derivative with respect to y of 0. Now, if I work this all out, this right here is just going to give me 0 because partial derivative of 0 is just 0, and partial derivative of x with respect to z is also 0. Well, we just got a bunch of zeros there. But this last one, though, is going to cause some problems. Because right here, if I take the partial derivative of x with respect to x, I'm going to get 1. But I'm not subtracting off of 1 here. If I take the partial derivative of 0 with respect to y, I get 0. So I'm left with 1 k hat. And that is not equal to the 0 vector. So this means that this particular vector field is not conservative. All right, which means that, by the way, there is no potential function to find. Okay, so that's pretty much all there is to that problem right there. Not bad. Okay. Let's look at a two-dimensional case because we had kind of a separate test for the two-dimensional ones. So if we have f equal to x squared y 1, and I'm going to call this guy right here, this is my first component, f1, f2, then what I want to check this time is that the if I look at my first component, it's y partial derivative. I want to check to make sure that that is equal to the partial derivative with respect to x of my second component there. So I'm going to compute fy for my first one, and looking at this right here, it's just going to be x squared. And if I compute f2 partial with respect to x, I'm going to get 0. Well, those aren't equal. So that means that it is not conservative, which means that there is no potential function to find. So basically what that means is that there's no function that it came from. There's no possible way to start with this vector right here and be able to work backwards to an original function. So that's really about all there is to that. Okay, so let's do f equal to y e to the 2x, and then 1/2 e to the 2x. So once again, we're wanting to check that if this is my f1, f2, that f1 partial with respect to y, we want to see if that's equal to f2 partial with respect to x. So my partial with respect to y of my first component here is just going to be e to the 2x. And my partial with respect to x of my second component here, that 2 is going to come down to the front, and I get e to the 2x. So they are indeed equal to each other, which means that I do have a conservative vector field. And since there's a conservative vector field, we can find a potential function. That means that we can find something that when we take its gradient, it gives us our vector field. So all we got to do is recover f from its gradient. And this process is exactly the same as it was before. So we're going to have that f of xy is equal to the integral of y e to the 2x dx, like so. So this is restoring all of our or our x information that we have. And in this case right here, I'm going to get 1/2 y e to the 2x. And then plus, well, we can't restore any information about y when we work with x. So we've got some unknown function in terms of y. So I can look at my y component here and integrate that with respect to y to recover this information, and I'm going to get 1/2 y e to the 2x, because that e to the 2x is just kind of acting like a constant since it's not dependent on y. And then this is plus some unknown function in terms of x. I'll call it c tilde. Okay. So, well, the thing is here that, well, we have basically the same function in each one here. fxy is definitely equal to at least 1/2 y e to the 2x. But we notice that neither of these contribute any new information that the other one doesn't have. So really the only thing that we haven't been able to account for would be some like little constant c. And this is our potential function. Okay, so for my last example, I wanted to do one that was a little bit more involved. So, but I'm going to have to turn everything kind of landscape so it all fits on the paper, which I guess probably sounds kind of ominous. All right, so in this example here, we are going to be looking at f, x, y, z equal to y, z sine of x, y, z plus 3x squared x, z sine of x, y, z plus 2y. And then for my last component, I have x, y sine of x, y, z plus 5z to the 4th. Okay. So we're going to check to see if this is conservative and then try to recover its potential function. So to check to see if it's conservative, we're going to check this guy crossed with f. And this is really the part that takes up the most room here because I want to make sure that it all fits on one line. This is equal to, so we have our I hats, partial with respect to x, and I'm going to put my x component from here, from up there, right here. So I have y, z sine of x, y, z plus 3x squared, and then I have my j hat, partial with respect to y, and then x, z sine of x, y, z plus 2y, and then my k hat, partial with respect to z of x, y sine of x, y, z plus 5z to the 4th. All right, got it to fit. Okay. So now all we have to do is take this determinant. So we're going to start with the I component there. And I'm going to get partial of y, or partial with respect to y of all of this right here. So and then minus partial with respect to z of xz, because now I'm looking at this right here. Sine of xyz plus 2y. So, and then this is going to be minus j hat times, and then same idea here. I'm blocking out this column, and we're going to look at partial with respect to x of this guy down here. So partial with respect to x of xy sine of xyz plus 5z to the 4th minus partial with respect to z of yz sine of xyz plus 3x squared. And then finally plus k hat of times partial with respect to x. And then this is going to be of xz sine of xyz plus 2y. And then minus partial with respect to y of partial with respect to y of yz sine of xyz, and then plus 3x squared. Okay, let's take all of these partial derivatives. So I have I hat times, and I'm doing the partial with respect to y of this guy right here. So we're going to have to apply the product rule to this first piece because I have a y here and a y inside of the sign. So I'm going to get x sine of xyz, and then plus derivative of this here with respect to y. I'm going to get x, y. Chain rule says that we're going to have x, z, and then cosine of xyz. And then, thank goodness, this piece is going to go away. So that's going to shorten it up a little bit. All right, and then we have minus. I'm going to open some parentheses here. Partial derivative of this with respect to z. So same idea, chain rule, x sine of xyz, and then plus xz derivative of this guy here with respect to z. I'm going to get xy cosine of xyz. And then close that bracket off. Okay, great. Now we just have to repeat that process for these next two. So minus j hat, partial with respect to x, I'm going to get y sine of xyz, and then plus xy derivative of this with respect to y, xz cosine of, oops, this should be a yz, cosine of xyz, and then minus, open some parentheses, taking this partial derivative here with respect to z is going to give me y sine of xyz plus yz times derivative of this guy with respect to z, so xy, and then the cosine of xyz. There. Okay. And then finally, k hat. I'm going to have derivative of this with respect to x. That's going to give me z sine of xyz plus derivative of, so we have xz derivative inside here with respect to x, y, z, sine of x, y, oops, nope, cosine x, y, z. And then, oh, I guess I didn't mention here, I mean, these pieces both go away because you're not taking, or you're taking the derivative with respect to a variable not present in this little term here and that little term here. The 2y also gets to go away for the exact same reason. And then we have minus derivative of this guy with respect to y, and I'm going to get z sine of x, y, z, and then plus y, z, and then derivative of this guy here with respect to y, x, z, cosine of x, y, z. Whoa. Okay, well, that all barely fit on the page. I'm kind of moving my page out of the field of vision here. So anyway, it kind of looks like a big, huge mess, but it actually cancels out really nicely. Because if we look at this I hat here, we have x sine xyz here, and there's a minus x sine xyz here. We look here, we have what's effectively an x squared yz cosine of xyz, and we have here x squared yz cosine of xyz. So that goes to 0. Same idea with here and here. Those two terms completely all align, and then they wind up being, there's that minus sign in there, so you get 0 I hat plus 0 j hat plus 0 k hat. Just like so. And I mean, it's a lot of work. It's a little bit tedious, but it pops out to be 0. So that's kind of nice, right? Okay, so we got it to be 0. What does that mean? Well, our vector field is conservative. And we need to find a potential function that it came from. So such that f, our original vector field, is equal to the gradient of that function f. So we're going to recover f from its gradient, which is equal to capital F. So I'm going to rewrite capital F here. It's y z sine of x y z plus 3x squared, x z sine of x y z plus 2y, and then my final component is x y sine of x y z plus 5z to the 4th, just like so. Okay, so the function that I'm looking for, f x y z, has to be equal to somehow the integral of our x component here with respect to x. And taking this integral with respect to x, the result that I'm going to get will be negative cosine of xyz plus x cubed. And then we weren't able to account for y and z here, so we're going to add on to it some function in terms of y and z. And we can recover information about this by taking the integral with respect to y and z. So I'm going to look at my y component here, take its integral with respect to y. And I'm going to get negative cosine xyz. 2y, so plus y squared, and then this is going to be plus some unknown function in terms of x and z, because we can't recover information about x and z using an integral with respect to y. And finally, we complete this picture using our integral with respect to z of our z component. So xy sine of xyz plus 5z to the 4th dz. And what we get out of that then is going to be, again, the negative cosine xyz, but this time we're going to add on to it z to the 5th, plus some unknown function in terms of x and y. So putting all this information together, I noticed that they all have that negative cosine xyz in common. So that's definitely going in there. It only goes in there once. We're not just simply adding everything together. But then we see, okay, well, we have this plus x cubed here. And then this allows for some unknown function in terms of y and z. And that's where the y squared and the z to the 5th come in. And then just double checking to make sure we got everything. This says an unknown function in terms of x and z. Well, we already got the x cubed and the z to the 5th. And then same idea here in terms of x and y. We already got the y squared and x cubed. So this would wind up being our final answer for the potential function for f. So yeah, that's pretty much all there is to it. Again, big idea here to walk away with is that if your vector field is conservative, we can figure out some function that it came from using its gradient. So just kind of remember that big idea there. So yeah, I'll see you guys next time.